Welcome back, everyone, to the second half of Tuesday for our double categories workshop. It's my great pleasure to introduce Bojana Femić, who will be speaking today about grade type monoidal product and Bifunctor theorem for double categories. So take it away.
Thank you, Bryce. So in the first place, I really wish to thank to Bryce and team for organizing this workshop. They're so young and so already capable of doing this great job. So thank you, and thank you for inviting me to speak here. Well, actually, I consider myself very new to double categories. So if you can see on the top, I have 4 parts of the talk in the top. I don't know if now. Yeah. So mostly it would be expository talk, and just the final, this one that says Bifunctor Theorem, would be something new. That is my latest work on archive. Okay, so here is the overview of the talk. Well, I will start by defining double categories, although everybody now knows, but I think that when other people add their vision, it adds to the richness. Then I want to present this construction of the double category of monads due to Fjord, Bino, and Koch. So these days we have heard already a few versions of such double categories. They seem to be all different. And we will see why vertical morphisms in this particular double category are useful. And then the second part treats the grade type tensor product on double categories. This first item here is the grade type product in the category of double categories and double functors. I mean, strict in both cases. And this construction was due to Gabriela Böhm. And then comes this last part, which I call Bifunctor Theorem, where actually I will show few different related results. And all this part was inspired by the recent work of Paul, Manuel, and Siqueira. They did this construction for 2 categories. Then I lifted 2 double categories. Okay, so double categories, let's start. I cannot speak about double categories without mentioning bicategories. I'm not going to give a definition, but here is my visual presentation. I think of bicategories as that we have these 3 levels of data, 0, 1, and 2 cells. And now, in contrast to this, when we pass to double categories, then I present on this diagonal the bicategory or the horizontal bicategory of the double category. So there I will have 0 cells, horizontal 1 cells, and squares, which I often just call 2 cells. And here on diagonal, I put these vertical 1 cells. This is how I think of them visually. But now formally, a double category is an internal category in the category of categories. That's what Bob said yesterday. And he showed 1 presentation. Christina today showed one that resembles mine here. Well, what it means to be internal in any ambient category? Well, it means to have 2 objects. One is called object of objects, other object of morphisms, and then 4 morphisms in the ambient category. In this case, there are 4 functors: source, target, unit, composition. The base category should have pullbacks, and cat1 has them. Now, this composition should be strictly associative and unital. But what does this have to do with the visual presentation from the previous slide? I add also this line at the bottom. So C0, the category, that will be vertical category for me. It consists of 0 cells, has them for objects, and vertical 1 cells. And the C1 has horizontal cells for objects and squares for morphisms. And we can see them here. So source and target map from the, so to say, right hand side category C1 towards the left, C0, giving us, well, for horizontal maps, source and target give domain and codomain, and for the squares, the vertical 1 cell, which is domain and codomain of the 2 cell alpha. Okay, maybe I could skip this because, yeah, so far we know all, but okay, just little things more. This composition gives us the horizontal composition of, okay, so horizontal 1 cells and particularly of the squares. And the fact that C1 is a category gives us, among other data, gives us that the composition of squares in the vertical direction. So it gives the vertical direction the composition, and it is strictly associative and unital. Okay, so this is the strict case, strict double category. And on the next slide, I speak about the weak case. It is called pseudo-double category. Formally, it is a pseudo-category internal in the two category of categories. Shortly, I just say it internal in Cat2, because saying the dimension of the ambient category tells me that I'm weakly internalizing and not strictly, so to say. Well, as before, we have two categories and four functors. But what differs now is that now the composition is not anymore strictly associative and unital, but we have natural transformations. There are two cells in this two category Cat2. Actually, there should be isomorphisms, alpha, lambda, and rho, satisfying the usual pentagon and triangle. Here is an example of, for me, like the base example, most famous, the bicategory, whose 0 cells are algebras, 1 cells are bimodules, and 2 cells are bimodule morphisms. But when considering this bicategory, we are excluding something very important, or one basic algebraic gadget, and these are algebra maps. So if we want to include them in the picture, then we should really consider the pseudo-double category, where on the diagonal I put this bicategory above, and off diagonal I add algebra morphisms. Now they change us a little bit the 2 cells or the bimodule maps as follows. So in this square in the vertices I put algebras, on the horizontals are bimodules, and on the verticals are algebra maps. The square alpha should be some kind of bimodule map, while above M is an AB bimodule, or BA, it's the thing of convention, and below N is an A prime B prime bimodule. But then we all know that along the algebra morphisms F and G, N can be made into an AB bimodule. So then AB bimodule maps between M and N in this way via F and G are considered these bimodule morphisms in this picture in the pseudo-double category. As Paula said yesterday in her talk, in this example, we can get the intuition that in every pseudo-double category, there is a bicategory. So you can just restrict so that the vertical 1 cells are identities, and correspondingly, the 2 cells will be globular 2 cells, or of this form. So they are non-trivial, but just the verticals are identities. And this bicategory we call horizontal bicategory of the pseudo-double category. So it's the same notation as Christina had in her talk. Well, so far you could see that I do it as Christina and opposed to what Bob did and how Matthew did yesterday, that my horizontal direction is up to isos and vertical is strict in the sense of associativity. And the other way around, every bicategory can be embedded into a pseudo-double category by taking identities of the verticals. Here I want to add one more fact that was proved by Bob and Marco, that every pseudo-double category is double equivalent to a double category. So we have the stratification result, that is great. And they also prove that every pseudo-double functor can be stratified, but you cannot do it with lax or collax double functors. So it is good to know. And here about functors among double categories, I just listed some which I will mention in this talk. We have strictly double, three-double functors, pseudo-double functors, and lax or collax. Bob gave yesterday a definition, but here I want to stress visually. So what is the strict version? If it concerns the compatibility of your functor with the composition of 1 cells, of horizontal 1 cells. If these two are equal, you will speak about strict double functor. If there is an isomorphism, the globular 2 cell, you speak about pseudo double functor. And if there is a 2 cell from top to bottom, you have lax double functor. And the other way around, you have collax. There are also double pseudo-functors that Schulman treated and Gabriela Böhm, but I will not mention this example in this talk, so I didn't list it here. Okay, the second part is about one illustration why it is good to work with double categories. I mean, we are seeing these days very nice and many examples of why it is nice to work with double categories. But here is something that I prepared. This is construction due to Fiore, Gambino, and Koch. But the title here says why the two category of monads in a two category is not enough. Okay, for something that I'm going to say. On this slide, I put the definition of the two category of monads in a two category K. It was introduced by Street in the 70s in this paper Formal Theory of Monads. We'll go just quickly over zero cells, but one cells are where I want to put the stress. So T is a monad on A. So A is a zero cell and T is an one endocell on A. And there are two cells multiplication and unit, associative and unit, okay. And now morphisms between two monads, T on A and T prime on A prime, are something a bit strange. They are pairs, where X is a one cell from A to A prime, and psi is this kind of two cell. And this psi needs to satisfy these two laws, which are actually like distributive laws of psi with respect to the multiplication and unit. I looked at my string diagrams from top to bottom, and there are two versions. As Bob said, you can consider lax or collax monad maps, or left or right, as you want to see it. And okay, now two cells, I'm not interested in them now. Many authors have seen that different algebraic structures, like for example, categories, operas, multi-categories, T multi-categories, can be seen as specific monads in appropriate bicategories. But one also observed that many times morphisms between such things are not monad maps in the sense of the previous slide of the definition of Street. Two more examples here that Matthew mentioned yesterday. Internal categories, there is a variation with a discrete object of objects. They are monads in the bicategory of spans in a category V which has fullbacks. And respectively, in the discrete case, we have this variation with sub D. The difference here is that in the usual bicategory, the objects are the objects of the category V, while in the discrete case, the objects are just sets. The other example, enriched categories are monads in the bicategory of matrices, but monad morphisms between these monads, so in the bicategory spans and the matrices, are not the morphisms that we are hoping to have. So they are not internal functors, or respectively, they are not enriched functors. So in order to come out of this, to address this issue, Fiore, Gambino, and Koch in this paper defined the double category of monads in a double category D. It consists more or less of this data. So for zero cells, there are double monads. I put this in parentheses because they are just, it's the same as in the talk of Matthew yesterday. There are just two monads in the underlying bicategory of D. Horizontal monad maps are the same as in the definition of the two category of monads of Street. So on the vertical cells, we will have just identities. But what is new here are these red parts. So vertical monad maps are new. So it's the same as Matthew introduced yesterday. And squares are then, okay, correspondingly new, but I'm not going into them. Now having this kind of, this double category, this allows to describe mathematical structures and morphisms among them as monads in appropriate double categories and vertical monad maps. So in view of this double category of monads. So at this place, I can say that I don't remember maybe with certainty how it was for Matthew, but I think that these, what here are vertical, maybe for them were horizontal. And then for the other ones, he added the retro, which I'm not speaking here. Yeah, Bryce was the cause, so you know, better than it. And so now here I want to put a definition of vertical monad maps. So these are these squares alpha. So this is the same as Matthew showed yesterday, but the direction of horizontal and vertical is the opposite way by definition. So here, vertical monad maps are given by squares alpha. So it is a vertical monad map between one monad T and another T prime, whereas on the verticals there is a vertical one cell U in the underlying double category D. And then it is the same to apply twice alpha and the multiplication of second monad, or firstly multiplication of the first monad and then alpha, and then this law for unities. It is actually a very natural definition. And now going back to our example of internal and enriched categories, with this definition you really get, and it is easily seen, and we also commented in my joint work with Enrico Ghiorzi, and it is on archive, that 1V cells, so these kind of vertical monad maps, in this double category of monads, in the double categories of spans in V, they are indeed internal functors. So span on the previous slide was a bicategory, but Fiore, Gambino, and Koch turned it into a double category. And in the other example, 1V cells in the double category of monads, in this double category of matrices, are indeed V-enriched functors. So again, on the previous slide, we spoke about bicategory of matrices, but we have enlarged it into a double category, and this works nicely. Okay, so that was just like to mention why it is nice to work with double categories and to see monads and double monads. And now I go towards this topic, this other topic, which is the great tensor product on double categories. Now, because the audience may be very varied, I included here the definition from the basis. So what is great tensor product? If you have a monoidal category, great tensor product gives you a closed monoidal structure. For a category to be closed, we have left and right definition. Here I wrote down the right version. So here C is the monoidal category, and here is just the home set between morphisms of this type are one-to-one correspondence with those of this type. This is the inner home. Isomorphism should be natural in X, Y, and Z, and we have an adjoint pair of functors. If X is tensoring on the right, we have left version of closedness. So both should hold for a closed category. Now, in every closed category, one has this composition morphism in C on the home functors. So this is really like in the example of the category of bimodules over algebras. This is really the composition of the home sets. Now, if for this category C, we take particularly the category of two categories and two functors, the natural candidate for the inner home is the two category of two functors between two categories A and B. Since this should be an object, if the category and category is that of two functors, then this should be a two category. The three levels of data are two functors, Lax natural transformation in this case, and modifications. But it happens that the natural composition that you can define among these two categories, it is not a two functor. So it should be a morphism inside here. So a two functor, but it fails to be a two functor. Why is this? So all the one cells in these two categories, which are now Lax transformations, they compose nicely. The two functor condition of the coherence of C on the composition of one cells translates into this interchange law in the strict way, because we are here thinking of the Cartesian product. But this interchange law doesn't hold in general for Lax transformations. If they were strict transformations, then yes. But in this version, this fails to be the case. So to come out of this, the idea of Gray was to look for a two category A tensor B. So we don't know what this tensor should be. such that, and then you write out the definition of the closedness condition. You don't know what the left-hand side is, but you do understand the right-hand side. So then a description of this tensor product is obtained by seeing what a two-functor on the right-hand side is. If you evaluate f at some b in B, you get a functor here. I mean, a two-functor. So then you need to evaluate again on an object A in A and so on, and also on the other levels of data. So you get a bunch of information there, but you can reorganize all this information into form a new definition of, so this is due to Gray, quasi-functor of two variables on the Cartesian product. And it is defined by reading out the relations that hold on, so when you evaluate here. And then this gives the sense how one should define this new product, this new, this tensor thing, by generators and relations. So you start from the Cartesian product and you put these relations that you found here. The most striking relation that differs from the Cartesian product is the one here. So if instead of the tensor signs, you would have commas in the, so these capital A and B, they are identities, F and G are one cells. So if in the Cartesian product, both sides would just be F comma G. But in the Gray type product, they are not the same. And since we work here with two categories, there is a non-trivial two category. In one or the other direction, there is a choice. And then Gray proved additionally that, so far we have existence, but he also proved that this gives you a really monoidal product on the category of two categories. So this is the construction due to Gray on the category of two categories. Now, what about double categories? In this paper, Gabriela Böhm, so as she said, to her knowledge, she was the first to introduce in this paper a Gray type monoidal product on double categories. So this double is this means strict double categories and strict double functors. And she introduced this tensor product in the following way. She starts by defining this inner home. So it is a double category. Bob and Christina mentioned it, but she defined it in a particular way. There are, versions of how you can do it. I'm not going to show it now. And then she proves that this is a bifunctor, so a functor in both variables. And then she uses a recent result by Burke and I don't know if Garner or Gursky, that the functor on the right-hand side, it is enough to show that it is representable if you show it on generators. So by this kind of argument, she obtains the existence of this tensor product. So she doesn't do it by generators and relations. In this paper here, I then, for some other things that I wanted to do, I follow the Gray's recipe, so to say. I characterize the double functor into this inner home. And I read all the structures there and the relations which would define these tensor products that we know that exist. Okay, so this finishes. I just wanted to show this as a how you search for this Gray type tensor product. This finishes this expository part, and now I would go to the last part, which is about the Bifunctor theorem. But let me say now that at the beginning of this last part, I'm also going to address the question of searching for a Gray type tensor product, but in the variation of this category where instead of strict double functors, I consider lax double functors. So I was not aware of any maybe conceptual arguments, so I did it by hand as I describe now, and I saw that I cannot get it. So any shorter argument is welcome, but let me show what I did. So okay, here comes this last part, and it is, as I mentioned, inspired by the late work of Faul, Manuel, and Siqueira that I
Sorry, Bojana, we've lost your audio.
Okay. Do you hear me now? Okay. Do you hear me?
Yes, we hear you now.
Yeah, I guess I get a message that my internet is not good. I'm sorry. Do you see and hear me now?
Yes.
Okay, great. Yeah, okay. Okay, so here I'm just following the construction that was done in, yeah?
Yeah, sorry, it's cutting in and out for me, but
Okay. It was done for, I lose the time. I lost the, until when should I speak?
So
Oh, I have a plenty of time.
Yeah, you've still got plenty of time, don't worry.
Oh, yeah. I guess that I hurried because like people spoke about many things before. So now I will finish before plan. Okay, so this first part is just to, so I was trying to build a great type tensor product in the variation of this category, strict double categories and lax double functors. So I start here by defining this inner home as a candidate, right? Candidate for inner home. And now I do say how I do it. So for 0 cells, I take lax double functors. What here is in blue is to stress the difference with respect to the construction of Gabi, of Gabriela. So in this place, she took strict double functors. Next, for 1H or horizontal 1 cells, I take horizontal op-lax transformations. And for vertical 1 cells, I take vertical lax transformations. Gabi in both cases took just pseudo transformations. And the modifications are something that involves, of course, both of these two on the top. So I can here make a small comment. So I commented at the beginning that we have these different kinds of double functors. And then I said that the thing is, the difference is that you have this vertically globular 2 cell. So it spoke about the coherence of the functor with the composition of horizontal 1 cell, okay? So following this line, one obtains these horizontal transformations. And if you do the same, but considering like horizontally globular, or I don't know what I said, so in one direction or the other, you get then vertical transformation. But I think that Christina already now in her talk also mentioned this kind of stuff without really defining everything, but just mentioning. And then lax or op-lax speaks about if you look from top to bottom or from bottom to top or left to right and or vice versa. Okay. Okay, so this is nice on the level of 0 cells or double categories. So we do have this double category AB, inner home. But now the problem comes when you want to have the great tensor product that this should be a bifunctor on your category. This one doubles the lax. And now here's the problem, because on the level of 0 cells, as I said, so it is above, it works fine. But then if you pick up morphisms in here, there are lax functors. So you pick up a pair F and G, they both are lax. Now you want to make this inner home FG, you want it to be a lax double functor. So don't even come to the laxity. It already fails when you want to define how this FG acts on, say, be it vertical or horizontal transformations. Because in order to define the image here, you do need both lax and co-lax structure of the functor G. So if you would have here strict or pseudo, you would be fine. But only on lax, you cannot define it. So this fails to be a bifunctor, and you should have it to have a closedness. But anyway, having this inner home on the double categories, one can still characterize a lax double functor into this gadget. And you get a bunch of data and you reorganize them following the recipe of Gray. And this gives me the definition of what I call Lax double quasi-functor. At this place, I want to show you just a definition, just like to, not to impress, but you know, when you work with double categories, you need a lot of paper and a lot of patience, a lot of space. So here is the characterization. This is just cuts of the paper. A Lax double functor of this form consists of the following data. So you have inside two Lax double functors, one of this form, another of this form, so that on the zero cell they coincide. And then you get these four kinds of double cells. So the top and bottom are two types of globular cells, and these are some mixed types. And then you have 3 A4 pages of laws that should be satisfied. So this is just to show you how it looks like. So here are some which are purely horizontally. But then you have also involving vertical cells. And here. Okay. So we have these four types of cells. In the case of Gray, who treated two categories, you only had this first type of two cell, right? So these other three, of course, did not exist there. Okay. And then having these relations that one gets, that I show now, one can define this kind of product. Well, I really don't know if it has any sense to define it, because so how Gray proved that this thing for two categories is a monoidal product is a bit, I could not understand it completely. So I wanted to follow what Gabi did. But what Gabi did fails in the case of Lax functors, Lax double functors. So I really don't know if there is a way around this to show it directly. I really don't know. So, but something like this can be defined. I don't know if it has sense, because I'm not entering into if this is associative or anything of that. Okay, so now these Lax double quasi-functors, I organize them into a two category. And this I can also, since I have a lot of time, I can also just show, so not really to read the definition, of course, but just to go like shortly on top of it. So one cell should be, this HOP stands for horizontal oplex transformations. And then there are four types of axioms. So this is HOT for horizontal oplex transformation. And then Q for quasi, HOT Q. So there are four. So this first one is the same one as for two categories. And then we have these more. This number 2, number 3, and number 4. And then also modifications. Oh, okay. So one defines, I define here the two category of them. And then I show that there is a two category isomorphism between these two categories and this other one. So these are Lax double functors, horizontal oplex transformations and modifications. Here I need to stress that, of course, here the composition of horizontal oplex transformation goes in the vertical direction. Otherwise, we cannot define it because we have Lax functors. And one can also show, just following how Gray did it, that there is also this kind of isomorphism of two categories, so that when you connect them, you get this thing that resembles what you want to have in a closed monoidal category. But these are two categories. So if you look only the level of zero cells, so you have a one-to-one correspondence between Lax double functors on the left and Lax double functors on the right. So you can formally, maybe this doesn't have any sense, but you can formally write that there is this isomorphism of sets. So this is what one would write if you would have closedness. But as said, I recall this is not a bifunctor. I don't say that this is a monoidal product. Okay, this was just like an exercise. And now I pursue with other results that Fal, Manuel, and Siqueira proved for two categories. This is about the Bifunctor Theorem, and this is the background that existed on one categories and two categories. For one categories, you may find it in Maclean's book. It is the first proposition there that given two functors labeled in this way, that both end up in the same category, so that you have this relation among them, then there exists a bifunctor on the product of the categories into D, so that the bifunctor is related with L and M in this way, if and only if there is this kind of commuting relation between L and M when they are evaluated in the morphisms of C. Moreover, this bifunctor is connected to L and M in this way on objects and morphisms. So as said, in this is the paper. In this paper, they leave this to two categories. And so in their terminology, it goes like this. Let sigma be a distributive law between families of Lax functors. So these are Lax functors among two categories. I'm not saying what distributive law is, but actually this is nothing but the quasi-functor in the sense of Gray. Then there exists a Lax bifunctor satisfying, okay, so these compatibilities with the partial functors, and this new one on the two cells, this is the horizontal composition of two cells, so that this distributive law sigma permits you to define the Lax functor structure on P. So on the compositor and the uniter for P, you get from the uniters of L and M. So then moreover, there is this, they speak about these two categories of distributive laws, and they make a two functor to this category. So this is to compare with functors on the Cartesian product. And this is what is called the Bifunctor theorem. So you get here, you have here a pair of functors or family, a pair of families. And you assign them just a functor on the Cartesian product. So this is the name Bifunctor theorem, refers to that. They also study when this K restricts to equivalence. And now this is the thing that I want to lift to double categories. But in my terminology, I put it like this, QLAGs, because these are my LAGs double quasi-functors that I introduced before. And then I also prove that there is a two functor F into this two category of LAGs functors on the Cartesian product. To have an equivalence, you need to there is one thing that I didn't comment, and I think that this is, this is actually, sorry, this is the first place where I mentioned this NS in above. This stands for non-strong, and I'm not happy about this name. Strong means, so this is how Bob and Marco named the, say, be them horizontal or vertical transformations, which have these globular two cells, which are non-trivial. So it is called strong when you have these non-trivial globular two cells. And my NS here stands just for mnemonic, just to say that this type of globular cell UU, this needs to be identity in order to have a functor, a two functor, which ends up in this category on Lax functors on the Cartesian product. So this is a slight restriction that you need. And then if you want this F to restrict to equivalence, you need also to specify more. So you need to take full sub-two categories. This U stands for unital, so that the uniters are invertible. So these are quasi-functors. Remember that they consist of these two kinds of Lax double functors, so they have their uniters. So we require both uniters to be invertible. And on the right-hand side, you also take unital, but also this D stands for that the compositor of this type should be invertible. I mean, this is really technical, but when you do the proof, you see that you just really need this. And then you really get to equivalence. So in these restricted sub-two categories. Now, since this condition on the unitality and the decomposability here, if you switch instead of lax functors to pseudo functors, you would have automatically them satisfied. So then you can restate this in terms of the two categories where zero cells are pseudo-double quasi-functors on the left and just pseudo-double functors on the right. Okay, so here again, this is the Bifunctor theorem that connects the quasi-type functors with the functors on the Cartesian product. Now there is this story about carring and uncarring functors. This terminology, as I understood, comes from computer science. I really don't know much about it. I will just say how one gets to them. So this star is to tell that this is an isomorphism that we already saw before, but here I just add this NS just to tell you that I'm restricting to the case where this two-cell UU, which appears in the characterization of quasi-functors here, it should be identity. And here NS, when we define this inner category, double category, this inner home, we had those also vertical transformations, and we need those there, UU, to be also identity. Explain what it means on the right-hand side. Now composing this isomorphism with the two-functor F from the previous slide, this yields this kind of functor, which is called an uncarring. So as I understand it, why they put this name uncarring, so on the left you have this, how I would say, iteratively given functor. It is a functor which ends in something which is a functor that you again need to apply somewhere. So from there you kind of open it up and you end up in a functor on the Cartesian product. So this is the uncarring. For the other way around, with respect to this isomorphism, we restrict by taking unital things as needed, and then you compose with the equivalence F prime from the previous slide, and this gives the carring two-functor. So as said, the authors proved it for two categories. So these are two categories, but the gadgets inside are double categories. And this is the final slide. This is to say tiny application to monads in double categories. So to start with, remember that Benavou has observed that a lax functor from the trivial two category into any two category is just a monad in your two category, in the codomain two category. Well, then it is immediately seen that the same holds, the analogous holds for double monads. So I just record this fact for double categories, but actually you can lift it. I mean, you can see the same for the whole two category of these lax functors from the trivial double category to any double category D, with horizontal oplex transformations and modifications. So these two categories are isomorphic to the two category of monads in the horizontal B category of D. So I gave you the sense on the level of zero cells, and the rest is not difficult. And even furthermore, we have this isomorphism. So this is the two category from the previous slides, but now just the domain double categories are trivial. And on the right-hand side, we have these two category monads, the two category of monads of H of D. Why is that? So I just explained it on the level of zero cells. So a quasi-functor, lax double quasi-functor, as I said here, consists of these two kind of lax double functors and bunch of data. But now in our case, these domain double categories are trivial. So looking here, this B is trivial and A is trivial. And then remember this first sentence, you just get monads in D. So on the left here, you already have two monads. And also here, the only non-trivial thing that you get is this double cell. So this will be your distributive law, so you kind of just translated it into another language, and you got two monads and a distributive law, and it is indeed a zero cell in here. Okay, and you also can do the analogous argumentation to see the isomorphism on the level of 1 cells and 2 cells. Now, these two isomorphisms of two categories, I will put vertically in this square that follows. So here and here. On the top, I put the two-functor f, recent two-functor. Here it ended up in the Cartesian product of the trivial double category, but of course, it's just the trivial double category itself. And what happens below? So already street notice that this M and D, it is actually a functor from the two category of two categories from the category of two categories into the category of two categories. And there is a natural transformation comp for the composition of monad with monad. Okay. And now what is interesting for me to see is that this F, when you apply it to the trivial double functors in the domain, you recover this composition of monads. So that then you see that this F speaks a lot more than just that. Okay, so this finishes the talk. Thank you for your attention.
Thank you very much.
So any comments or questions? So as I said, I have some uncertainty about this gray product in the case of strict and lax. And to me, somehow it smells to this that you can strictify pseudo things, but not lax. But I don't see, you know, a direct. I really don't know if there is some shorter argument to say like leave it, you will not get it. I don't know.
Oh, I have a question, if that's okay. Can you hear me?
Yes.
Okay. Yeah, thank you for that great talk. Yeah, I was especially interested in this link between the gray tensor product and our work originally. So I have, it's potentially quite a naive question, which is, yeah, in our original paper in the two category setting, when we expressed the laws that these, what we call distributive laws, needed to satisfy, they had quite an intuitive explanation given in terms of string diagrams that had these nice distributive properties, and you could kind of link them between braidings and distributive laws of monads in that way. And so I wonder, is there any way to do this in the double category setting, something like that?
You know, I was also thinking about that, because we know that when we speak about, when you express yourself in string diagrams, where I'm kind of a fish in the water, you're missing these, like, what's happening on the side here? I mean, if you know what I mean, if you write squares, then on the side you have these verticals, as I say, but here you don't. So I was thinking about adding some kind of special boxes, or I don't know, but I really didn't invest a lot of time of thinking about that. But yeah, I like that idea. Yeah, so since I already worked with double categories before hearing Manuel's talk, I was like, oh, but that rings a bell. That's very, you know, similar what I did. And yeah, but because I worked with double categories, I needed to express myself with the squares. But it would be interesting to see what happens here.
Oh, okay, thank you.
I can also ask you if you, I mean, the three of you, have you thought about this question of gray product? Because like you do many things around it, but you just don't do it.
Yeah, well, I can confirm that, yeah, I was kind of unaware of the link between the gray tensor product and the work we were doing. At least, yeah, I was quite new to two categories actually in this paper. So yeah, that was kind of news to me. I'm not sure about my other co-authors, but I think it might be the same.
Yeah, like we knew that there was, like, we didn't really know exactly very much about these kind of non-strong versions of the gray tensor product. Though I did at one point just check whether it was precisely the usual like non-strong versions, and I saw that it wasn't exactly the same, but we didn't really know the exact link. So I think your description has helped us, I think, to understand the link better than we knew. Of course, there is, I know you cited it in your paper on the archive, the strictification tensor product paper.
Branko Nikolic or what? No,
yes, exactly.
Cited it. Right, I was third. Yeah, okay, tell me.
So that, I think, I mean, that kind of is the tensor product, I guess, version.
Yeah, but sorry. I wondered, like, is there a link what I wanted to do and what he did? But then, so when you see what he does, he takes the two category of legs, these legs functors, op transformations, modifications, and so. And on the right-hand side, he gets this inner home, which, as he explains, these are strict, not double, sorry, these are strict two functors. And what I'm doing here, I again want to have legs functors,
yes,
but on another gadget. So, you know, it looks like he's doing what I want to do, but no, he really does something.
Okay, yeah.
Yeah, so it's here, right? So instead of writing here legs, he has other sign because it stands for strict two functors. Yeah. And then he gets another, yeah, I don't know to which level I should watch, you know. So he gets another product which is constructed in some completely different way that I don't understand, but it's really different stuff.
Yeah, I know. Certainly, yeah, there are many kinds of these gray type products, and many of them involve this additional strictness. But yeah, there seems like there should be some relationship, but I don't know exactly.
Yeah, it would be nice if somebody, you know, has a larger scope to tell us all.
Any other questions? Maybe I have a sort of a semi-naive question, which is that so for the gray tensor product on 2cat, you sort of find this interesting sometimes because then you want to enrich with respect to this gray tensor product on two categories. Have you thought about doing things along these lines for the gray tensor product of double categories, enriching in with respect to this monoidal product?
I really didn't do, I cannot say anything, but I didn't do much with enrichment, no. So
Okay.
I never really explored in these waters. I have studied the relationships between internalization and enrichment, but this is something that is an interesting direction to think. Thank you.
Okay, thank you. Okay, well, if there's no further questions, let's thank our speaker again.